Hello Chem 1B, this is chapter 18, lecture video 3, and we're going to start talking about what we call standard molar entropies. Now, standard molar entropies are primarily used in Hess's law's equation for delta S of our reaction. If you remember from Chem 1A, there was an equation that we used to calculate delta H of reaction, and it was delta H of reaction is equal to the sum of the delta H naughts of formation of the products minus the sum of delta H naught of formation of the reactants. And this equation is effectively what we're going to be using these S naught values in, right? Just replace S naught with delta H naught of formation and H with delta S of our reaction. And we can use these to do that, and that's the primary use of them. Now, one of the things you should know about some of the S naught values is that they change with various different things, right? So for instance, the structure of your solid can change your S naught value, right? Carbon has two structural states. It's either graphite, which is pencil lead, or diamond, which, really expensive. And graphite's S naught value here is slightly larger than the S naught value of diamond, and this is due to the structural component. Graphite is a way less ordered solid than diamond is, and then therefore so its S naught value is just slightly larger because there's a little bit more disorder in the graphite solid structure than the diamond solid structure. The other thing that affects our S naught values is physical state. As we go from the solid state to the liquid state to the gaseous state, we see our S naught values increase as we go towards the gaseous state because gases are way more disordered than liquids or solids. Gases are bouncing around all over the place in constant motion and therefore way more disordered. And the final way that this changes is with complexity, right? If we look at this compound, it's made up of carbon and hydrogen for all three of these. But as we go down this table, we see that, methane is the simplest carbon-hydrogen compound, and then we have ethane, and then we have propane. And as we go down, we see that the size and structure of our molecule is becoming more complex. We also see that the S naught value is also becoming larger because more complex means generally more disordered. Now, you might notice that there is no negative S naught values in this table, and that's most of the time true with the exception of ions. But this is due to the fact that unlike both internal energy and enthalpy, there is actually a set reference point for entropy, and that is a perfect crystal at 0 Kelvin, absolute zero. In that scenario, we define that as being an S value of 0. So your standard molar entropy for a perfect crystal at 0 Kelvin is 0 and therefore has no disorder. And for that reason, generally, with one small exception of ions, which we're not going to focus too much on in this chapter, is that almost all of our standard molar entropies are positive. All right, so let's continue on. Right, so again, one of the big deals is that the S naught values for solid versus liquid versus gas. Solid and liquid are relatively similar, but liquid is definitely a little bit larger. Gases always have much larger entropy values. And this is because they're in constant movement, right? They're bouncing all over the place. They're crazy disordered as a sample. Whereas liquids, they're moving a little bit, but they're not moving as much as gases. And they're only moving a little bit more than solids. Solids vibrate a little bit, but they don't move pretty much. So entropy decreases as we go from a gas to a liquid to a solid. And generally, what this means is if we form a gas as a product, that usually will lead to a positive delta S for that reaction because from solids, right? If you're going from a gas to a gas, it's not as big of a change. But if you're going from like a liquid or a solid and you form a gaseous product from those, then you're going to have a large amount of disorder on the product side, and therefore your change in entropy will be positive as well. And we'll talk about how to calculate all that in a second.
Again, molecular complexity has a role here as well. You can kind of see methane has 4 hydrogens, 1 carbon. Ethane has 2 carbons, 6 hydrogens. Propane, 3 carbons, 8 hydrogens. And as you can see, as we go down this kind of chart here, our entropy S naught values, standard molar entropies increase. And this is due to the complexity of the system. It can be more disordered the more complex it is. So let's talk about standard molar entropies and what we can do with them. Primarily, we look these values up. Just like we did our S naught or our delta H naught of formation values from the last semester, we look these values up and we use them to calculate usually the entropy change over a process. The units of standard molar entropies is important to note as well. This J, joules, is important because a lot of times we use this with delta H's. And if you remember, delta H's generally have units of kilojoules per mole. Kilojoules and joules, they don't play nicely with each other. So we need to change the units generally. So it's just something that you're going to need to kind of pay attention to. Like I said here. Standard molar entropies of elements are also not 0. This is a big deal. For delta H naughts of formation, and there's 0 for an element in standard state. So O2, for instance, gas, is an element in standard state. Delta H naught of formation for this guy would be equal to 0. But this S naught is not 0, and it should not be. So just like with delta H naughts of formation, though, we can use S naught values in that same Hess's law reaction or equation to solve for our entropy of a process. In other words, generally the process we care about, since we're taking a chemistry class, is a reaction. So if I want to figure out, hey, did my reaction lead to more disorder or less disorder, then I can calculate delta S naught of our reaction by using Hess's law, which is this guy's sum of, and then we got products here, reactants there, and these guys here, the N and the M, are our stoic coefficients. We've used this equation before. Now we're just using it with S naughts as opposed to delta H naughts of formation. So again, entropy is a statistical measure of disorder. The more ways something can be arranged, the greater the entropy. So let's predict the delta H naught, or sorry, the delta S naught values, whether they're positive or negative for the following reactions. We don't actually need the values in order to calculate that. We don't have to calculate this to know, typically. Sometimes we do. Otherwise, we don't. For instance, here we have a liquid, and we're going to a gas. We know gases have larger S naught values. And what that means to me is when I do delta S of my reaction is equal to products minus reactants. If this value is larger, that tells me that this value is going to be positive. Or in other words, delta S naught of my reaction is going to be greater than 0. So let's look at another system. This one's maybe a little less obvious, but you also need to think about S naught or delta S naught as matter dispersal. That's really what's going on. Is my system more dispersed? In this case, we had two separate particles on the reactant side. On the product side, they come together to form one particle per every reaction. Well, is that disordered or more ordered? it's definitely more ordered, right? Because think about it this way. If you just throw your papers all over your room when you come home, that's going to be pretty disordered, right? Whereas if you took all those papers and stacked them in one neat stack on your table, that's way more ordered. Just like that here, if we have more reactants than products particle-wise, generally that means we're going to have a negative delta S naught for our process or reaction. And that is definitely the case here. Let's do a couple more examples. In this case, we have calcium oxide reacting with CO2 gas going to calcium carbonate. This reaction is going to definitely have a negative delta S naught. And for two reasons. One, we are going from two things, right? We have two reactants going to one product. But also, we're going from a gas to a solid. This is going to have a very large negative delta S naught of our reaction. All right, last one. Similar as the last one, negative, right? Because we have a solid here. We have 4 of them reacting with 3 O2s going to 2 products. So effectively, we're going from 7 things to 2 things. Well, that's definitely becoming a more ordered system, not to mention the fact that we have a gas here going to a solid product. So we can usually predict what sign we should expect just by looking at the reaction. And so kind of keep that in mind. That way you can look at your answer if you are doing an actual calculation and go, hey, you know what, this value does make sense or it doesn't. These are all types of what we call matter dispersal. So let's do, this would have been a clicker question, but which of the following reactions will have a negative delta S naught of reaction? So let's just kind of do this again, right? This was the one that I actually used on the previous slide. This is not going to have a negative value. It's going to have a positive value. So that's not our answer. If we look at this, we have 2. I should use a different color. Hold on. We have 2 of that. 2 of this reacting with 2 of this. They're both gases. So we have 4 reactants going to 5 products. All of them are gases. Well, 4 things going to 5 things, that's definitely more disordered. So we have a positive delta S. So that's not it. We have 4 plus 5 here. This is 9 things on the left side and 10 things on the right side. Again, this is more disorder, definitely positive. And they're all gases too. That's something we do want to look for. Okay, look at D, right? D, we have 3 reactants going to 2 products. Hey, that's less disordered. That's more ordered. This is going to have a negative value. They're also all gases, but because we're going from 3 things to 2 things, that's a more ordered system. This is our answer, as you'll see in a second. This one, just to kind of go through all of them, is definitely going to be positive as well, right? We have a solid. It's going to 2 gases. That's a big deal. Also, we have 1 thing on the left and 2 things on the right. More disorder. So again, D is our correct answer for that reason. All right, so let's do an actual calculation. Let's say I want to calculate delta S naught for a reaction. Let's say this reaction. We have H2 gas reacting with O2 gas to form H2O liquid. Now, if I was a betting man, I would predict this value that I'm about to calculate should be negative, right? I have 3 reactants here on the left, and I have 2 products on the right, because 2 plus 1 gives me 3, and 2 gives me 2. Not to mention that we're going from gases to a liquid. I'm going to say delta S here before I even calculate this is going to be a negative value. But let's do the calculation. We're just going to apply this equation here. So I know that I'm going to take S naught of H2O, liquid state, multiply it by 2 because I have this coefficient here. That's all my products. So that's the sum of my products minus the sum of all my reactants. Well, I have 2 from H2 here. And I need to use the S naught for H2, which will be some value that I need to look up. And I'm going to add that to S naught of oxygen, which I don't multiply. I guess you could multiply by 1 if you wanted. And so if we look these values up, the S naught for H2O liquid is 69.9. The S naught for H2 is 130.7, and the S naught for O2 is 205.3. If we do all that up, we add it, we get our S naught value is negative 327 joules per Kelvin. Technically still also per mole to the -1, but this is moles of reaction, not moles of any individual substance or reactant or product. This is a decrease in entropy. Again, we saw that probably from the beginning that 3 moles of gas going to 2 moles of liquid would be a more ordered system and therefore a negative delta S naught of our reaction.
So let's do one more calculation, one more example. We're looking at this reaction. 2 dihydrogen sulfide is reacting with oxygen to form water and sulfur dioxide. And we want to calculate the delta S naught for this reaction. Well, the first thing we need to do is we need to look up our S naught values. As you can see, we looked them up already here. At this point, we're just applying Hess's law, right? So products minus reactants, the sum of the products minus the sum of the reactants. Well, our products are H2O and SO2, and we have 2 of them each. So we got to take these 2 values here and multiply them by 2, as you can see here and here, and then we add them together. We're then going to subtract this from our reactants, which are oxygen and dihydrogen sulfide. And we need to multiply dihydrogen sulfide by 2 because there's a 2 here. And we need to multiply by oxygen by 3 because there's a 3 there. And that's where we get this 3 and this 2. We need to add them together and subtract it from the quantity that we determined for our products. So if we do that, you can see here's all the math, right? And plug in. Now we can subtract the 2. We get delta S naught of this reaction is negative, which we could have predicted, right? Because if we look at the moles of gas on either side of this reaction, we have 5 moles of gas total here, and we're going to 4 moles of gas, which basically tells us that the system is becoming more ordered, and more order for S naught of our reaction means that it's going to be negative. All right, so if you guys have any questions, as always, please email me or come to a Zoom discussion meeting, and I'll see you there.